Okay, so our next topic is called crustal deformation. So we're talking about deforming the rocks of the Earth's crust. Now we talked about the different types of rocks that we have, igneous, sedimentary, metamorphic, and sort of how they form. But then plate tectonics, right? So our movement of plates bashing the lithosphere together and stretching it apart and breaking it apart causes the rocks of the crust to deform. So here we have these are sedimentary rocks. You can see the layers in here. These are sedimentary rocks on the Colorado Plateau. This is the Colorado River down here. And you can see that sedimentary rocks are always deposited horizontally first. But we see that these rocks are not horizontal. They're actually, they dip down like this. They're folded, right? And we can see another fold that kind of does something like that. So this is crustal deformation, tectonic forces shaping those rocks. Okay, so to deform rocks, to do some crustal deformation, we need to put rocks under stress. So there's three main types of stress, and the first one is called compressional stress. So compressional stress happens when we're pushing rocks together. So we see these arrows here showing that we're pushing these rocks together. Here we have a convergent plate boundary, right? So we have the Indian plate, and it's being pushed into the Eurasian plate, and it's pushing up the Tibetan Plateau and the Himalayas. And so compressional stress is those plates are moving towards each other, pushing rocks together. It's shortening and thickening the crust. So the opposite of compressional stress is tensional stress. So with tensional stress, you see we're pulling these rocks apart. So here we have a rift zone, and this is on a continent, so it's a continental rift zone. And so the crust is being stretched and thinned. And so we see here, we see a series of faults develop as the crust thins. And here we can see that we've got thicker lithosphere over here on either side, and we've got thinner here. So we're pulling rocks apart, thinning and stretching the crust. That's tensional stress. Okay, so this diagram summarizes the kinds of deformation we get with different type of stress. Okay, so here on the left, the type of stress, here is our compressional stress. We're pushing rocks together, we're shortening and thickening the Earth's crust. Down here we've got tensional stress, where we're pulling rocks apart and we're stretching and thinning the crust. And we have another kind of stress called shear stress. And what shear stress does is it puts sort of unequal stress on rocks in one direction. So in this case, the rocks are kind of moving this way and this way. And so it deforms it more or less horizontal to the surface of the Earth. Now, when rocks are shallow, okay, so if we have rocks at shallow depths, those rocks are not under very much pressure because they're shallow, they're near the surface, and they're cool, right? Because remember, as we go deeper in the Earth, that geothermal gradient means those rocks are hotter at depth. So the rocks at shallow depths are cool, and because they're cool, they're brittle. And so if they're brittle, what happens is they fracture. So when rocks fracture, they basically break and split like this. And that is called a fault. So rocks fault at shallow depths. So if we have tensional stress, we get what's called if we have compressional stress, we get what's called a reverse fault. And if we have tensional stress, we pull these rocks apart. They also fracture and fault, and we get what's called normal faults. I'll go into those a little bit in another slide. And again, with shear stress, we get these sorts of faults at the surface called transform faults. Now, if we have rocks that are deep down, right? So if we have deformation deep in the Earth, those rocks are under more pressure and they're hotter, right? Because they're deeper down. And so there, the rocks don't fracture and cause faulting. The rocks will deform plastically, right? The rocks can fold. So we can see here we've got compressional stress pushing these rocks together, and we see a series of folds in here. So that's what happens when rocks are at deeper depths. Again, at deeper depths, if we have tensional stress, it kind of stretches and deforms those rocks, and at shear stress too, we get a deformation, but we don't get faulting. Okay, so let's talk about folding, and we'll talk about faulting in a little bit. So here we have a nice diagram showing some folds in some sedimentary strata. So we have sedimentary rocks here. Here's a limestone, and there's a sandstone, and a shale, maybe a conglomerate, and another sandstone here. So we have a sequence of sedimentary layers. And remember, sedimentary layers are always deposited horizontally first, because sediment that accumulates in low-lying areas gets deposited horizontally. So these sediments had to be deposited first, and then we have compressional stress folding them, so that when they're at deep depths, they'll deform by folding. And so we can see that these rocks are all folded like this in a series of curves, right? Now we have names. Geologists have names for everything. So an up fold like this is called an anticline, and a down fold is called a syncline. And so we get really interesting landforms when we have folded sedimentary layers. So number one, at a syncline, you see in the middle of this fold, if we draw a line here right down the axis of this fold, the youngest rocks are always, the rocks get younger in the middle, right? In the middle of this fold, we have younger layers. If we draw a line through the axis of this anticline, we can see that older rocks are pushed up. So we have older rocks in the middle of that fold, right? Deeper layers. Let me erase some of this. Okay, so we get really interesting landforms. Usually we get these long parallel ridges. So because different rocks have different capacity to erode, right? Shales are pretty soft and sandstones are pretty hard. So if we have sandstone right here, we have a sandstone layer, and then let's say we have a shale layer down here, we can see that the shale layer is going to make these valleys, and the sandstone layer is going to make these ridges. And that's because the exposed sandstone is more resistant to weathering, so it's going to stay up there as a ridge. Softer rocks are going to make valleys. So like the ridge and valley section of the Appalachian Mountains, you get these really cool long parallel ridges. Now the other thing about anticlines and synclines is if we look here, this is called the axis of the fold, right? Right down the middle here. So the axis is down the middle of the fold, and then the sides are called the limbs. But sometimes these aren't parallel to the surface of the Earth. So for instance, on this diagram here, we can see that not only is it folded in this direction, but it's plunging down this way. And that's called a plunging fold. And so you get really interesting sort of cone-shaped mountains and things from that. All right, to illustrate the process of compressional stress and folding, let me just give a little metaphor here. So I have a rug in my office on a hardwood floor, and I have this dog, right? And so if I get this dog really excited, he does some things to the rug. So let's say if I show him a treat, and he really wants this treat, he really wants this dog biscuit here, he'll start moving. He wants to move over towards the treat really fast, and he does his little doggy tippy taps, and that pushes the rug. It creates compressional stress on the rug and kind of pushes it, shortening it and thickening the rug. So we get something like this after the dog has come over to get the treat. And so you see, this is a nice corollary to anticlines and synclines, right? We shorten and thicken that rug, and so the up folds are anticlines and the down folds are synclines. Now, if we fold in two directions, right? So instead of just folding this way, but we also have folding this way, so again, in two directions here, if it's an up fold, we call that a dome. And we get structural domes. Usually what happens here is we have something like a pluton, right? So we have some igneous rock or some magma that intrudes into some sedimentary rock, and it deforms them in two directions. So you can imagine this oldest layer down in here is a pluton that pushed up, and it pushed these other layers out of the way in two directions. Now the opposite of that is a structural basin. We get a lot of these when we have glaciers sometimes. So we have the weight, you can imagine a mile-high layer of ice sitting on top of these rocks, creating a tremendous amount of weight and kind of down-warping them this way and that way. And then then you'll have surface erosion that might wear them flat, but you can see the rock layers are warped like that. In two directions, that's called a basin. Okay, so we talked about folds where rocks are at deep depths and they deform plastically and create folds. Let's talk about faults now. So faults, remember, if rocks are up close to the surface where they're not under a lot of pressure from overlying rock, and they're cool and they're brittle, then they will fracture in a fault. So here we have a fault. This crack going right down this road cut is a fault, and we've got a block of rock over here and a block of rock over here. We can see that they're offset. So for it to be a fault, you have to have the breaking of a rock body, and they have to be the rock body on either side of the fault has to be offset from each other. So we can see this dark layer of sedimentary rock over here is offset from this one, right? The top of this layer is up here, and the top of this layer is up here. So what happened is, erase some of these lines, what happened is this part of the rock has shifted down relative to this one that's shifted up on either sides of the fault, right? So we know we have a fault. Now, we need to know, number one, which side of the fault is the hanging wall and which side is the foot wall to know if this is a reverse fault or a normal fault, and that will tell us if we've got compressional or tensional stress. So let me walk you through how we figure that out. Okay, so imagine a lot of our terminology like hanging wall and foot wall comes from mining. So imagine we have a mine shaft that goes right into the face of this rock, right through the fault. Okay, and let's say we have a miner standing in that mine shaft. So here we have a miner standing here, and maybe he's got a little hat, hard hat to protect him from cave-ins. And then let's say he's carrying a lantern so he can see. He wants to hang that lantern on a hook. He'd probably hang it up here. Okay, so the block that he's standing on, right down here, over on this side of the fault, that is called the foot wall. Right, so this whole block over here on this side of the fault is called the foot wall, and the block that he hangs his lantern on, his lantern up here, that's called the hanging wall. Right, so on this side of the rock, this side of the fault, that is called the hanging wall. So anytime you need to know, does the hanging wall move up or down relative to the foot wall, you can draw your little mine shaft and your miner, and you can figure out which side's the foot wall and which side's the hanging wall. So here we can see that the hanging wall has moved down relative to the foot wall. So this is called a normal fault, and we'll talk about that in just a minute. Okay, so when you have faults that are offset, like in the previous image and on these diagrams, when you have faults that are where the rocks are offset vertically, that's called a dip-slip fault. Right? Because an angle of dip is an angle that goes down into the earth, and so we have rocks moving along an angle of dip. So here we have tensional stress pulling rocks apart. So the tensional stress is moving this way and this way. And so what happens is, right, here's the hanging wall over here, and here's the foot wall over here. And so the hanging wall is moving down relative to the foot wall. You can think about these rocks being pulled apart and the hanging wall slipping down. Now over here we have compressional stress, and so here we're pushing the rocks together, we're shortening and thickening the crust. So again, here's the hanging wall, and here's the foot wall, and in this case the hanging wall is moving up relative to the foot wall, right? So you can imagine these rocks being pushed together and the hanging wall being forced up. So when the hanging wall drops from tensional stress, we call that normal faulting. And when the hanging wall is pushed up by compressional stress, we call that reverse faulting. Now over here in C, we have a special case. Here we have a very shallow dip angle, and what's happening is, again, compressional stress pushing these rocks together, and what we have is thrusting of these rocks up over the top at a very steep angle, and that's called a thrust fault. Okay, so here's an illustration of a normal fault, and this can result in some interesting mountains up here. So our foot wall block stays up, our hanging wall block shifts down because we're under tensional stress pulling these rocks apart, and that's a normal fault. If we have normal faulting, we usually get a series of mountains because we're pulling crust apart, and so we get something like this. We get a whole bunch of normal faults in succession, and we often get what's called fault block mountains because the little scarps, the pieces that are left up, those footwall blocks, form a series of mountains. The mountains across a lot of the west through Nevada are fault block mountains. And then here's a reverse fault. So in this case, again, we've got compressional stress pushing the rocks together, shortening and thickening the crust. So the hanging wall block over here is thrust up relative to the footwall block, and so we can see mountains on this side resulting from that fault scarp.